Last semester I had that joke all the time, like it's impossible to get 100% on homeworks. I'm just going to throw the solutions up on the screen, I think. We work our time. Okay, so when I plug my computer into the display, it usually makes it crash, so we'll have to go without it. So looking at this homework, in number 1, we're finding tangent plane. So the hope is that this process is pretty straightforward for you on the exam. I did most of my work in MuPad, and then I just said the tangent plane is given by. So I think that this can be a procedure that you guys can employ on exams. Remember, I'm getting your VPAD file on homeworks and exams, so there's not really, to me, a need to rewrite all these things as long as you're clear on your VPAD file. Like, it's nice that some people write like number 1, number 2, so I can follow along, but even if you don't do that, it's in order or something, usually I can tell what's going on. So what I want to talk about here is ways that we can use MuPad to do our calculations. And there's 2 ways. The front page is the way that I've been doing it, and then the next page is another way. But let's look at the front page first. I'm too excited. So I defined f, of course, and then fx and fy. Those are the 3 pieces that I need in order to do tangent plane. And I'm interested in tangent plane at the point 2, 2, 10, which means x equals 2 and y equals 2. So I want to evaluate these functions at those points, and we talked about a natural way to do that is to define x and y to be 2. Then when I do fx and fy, those come out to be numbers now because those variables are defined to be numbers. And I do the step where I assign those numbers to other variables. So I call z0f, is like z0. I call mx fx, this is the slope in the x direction, and then my is fy, and you can see those 3 values there. And then I do delete xy. So I get those values, and then I delete x and y to go back into being variables. Because of course I need them to be able to write my linearization into graph. So you see the equation for the tangent plane there. Z equals z0 plus mx, which is my fx, of course, x minus 2, my, y minus 2. So this is the equation that we use for tangent plane, and it comes out already simplified and everything, my 17x over 2, 19y, or 9y over 2 minus 16. So that's my answer for the tangent plane. And then when plotting, I just plot those two things. I asked for a good view of tangency, which essentially means just zoom in. And I like to zoom in with the point of interest in the center. So I did x and y both from 1 to 3 because my point of interest is 2 in both cases. Some of you just didn't zoom in at all, and I said this is not a good view because I can't really tell if it's tangent or not. Some of you ended up with that point of tangency being in the corner, and I also complained about that because I think if we can't see all the way around that point, we can't really tell if it's tangent. It may look tangent from the one side, but maybe there's something strange happening on the other side. I think it's just good practice to be able to look all around that point of tangency. The last thing I want to say before flipping the page is that I complained to some of you about improper fractions, and this is just something that I tend to do. I think that the whole issue of writing like 8 1/2 to mean 8 1/2, I think that this is good for like elementary school, that students should learn it this way because it helps understanding, you know, what that concept means, but we shouldn't really use it right now. So we should write this either as 17 halves or as just 8.5. Fractions that come out nice are nice, and I can just use decimals. There's nothing wrong with that. If this was 8 1/3, well, I'm pretty much stuck not using decimals there because of, well, I suppose you could write this. You could write 8.3 with a bar over it if you wanted to, but for the most part, I would just stick with the full fraction, which is, of course, the 17. All right, so flipping the page, another way to do this evaluation of the function, which I just learned about right now. So there's this thing called, oh, I don't have it on this page. Let me just take a moment to get this up. It's going to take a while. Okay, so rather than defining x and y to be 2, we can use this substitution command. You see I did z0 equals subs f, x equals 2, y equals 2, and then the same thing for fx and fy. So this is something, where you don't have to do the delete x, because I'm not really, stop looking at this, it's not really that I'm defining x equals anything. If you look at the notation, it's, okay. We're just defining x equals 2, y equals 2 temporarily because it's equals without the colon, right? It's within the function substitution rather than being out on itself. So we're defining x equals 2, y equals 2 just temporarily in order to get that value, and then they go back to being variables. So in some ways this might be a more natural way to do it, but the writing, I think the amount of typing is pretty much the same. So both of these ways are really nice ways of doing these things, and I don't have to be sitting there doing the algebra on my own. I can use technology to do it. So I would recommend that you guys get comfortable doing this for the exam. I think it saves time, and I think it saves brain power, and it also saves some chance of making mistakes.
So you had to go down to work out.
That's right. That's right. Again, you're giving me the mu pad, so as long as the work is on the mu pad, you just maybe write down the final answer on the page, and that's fine. So my recommendation would be you guys are starting to work on suggested homeworks now because you don't have any homeworks to work on, and the exam's coming up here pretty shortly. So practice doing it this way. I think it's good technique, and I think it's not only good for now, but I think it's good is a nice way to be able to do things.
I open UPad, it does not work. Finally got this. I thought it was.
All right, so the next one, number 2, explain why it's differentiable, then find the linearization. So this one I do need to write some stuff down because I'm not going to put the explanation of why it's differentiable in MuPad, but of course I'm doing all my calculus in there, and I use the first procedure where I actually define x and y, and then assign those values to get my tangent plane, which is really the same thing as the linearization. It's just different terminology. But once I write down my partial derivatives, then I go ahead and immediately say, so I don't forget, that since those guys are continuous, f is differentiable. And I worded it in terms of being continuous at a point. Don't have to say that. If you just say they are continuous, so f is differentiable, then this means everywhere, so that encompasses the point of interest. And it is true everywhere. These functions are continuous everywhere that they're defined. And this is true all the time when we look at our functions. The only place where these functions that we can write down in nice ways will be discontinuous is really where they're not defined, and then we wouldn't even ask about continuity there. The bad kinds of functions are the piecewise defined functions. These are the bad functions, the ones that actually could be discontinuous. So there's not much work to be done here. Some of you are trying to give me work to show that it's continuous, and I just like to take a moment to talk about that. If we're talking about, for instance, this function fx, which is this thing. If we're talking about that function being continuous at the point 1, 2, by definition, it means that the limit as x, y goes to 1, 2, fx, xy equals fx, 1, 2. That's what continuity means by definition, that the limit is equal to the function value. But this is true because I can just plug in those points into this function because it's defined. And whatever number I get for that will be true for the left and the right. For the right because I'm plugging it in, and for the left because of direct substitution. So this is how we evaluate limits. The only time we have trouble doing limits is when that point is undefined, and that's why we use limits. So there's really nothing to check there. The point of us doing continuity for so long in the beginning of the semester is so that you maybe have an idea of what continuity means, and then I get homeworks like this and I think, well, we really don't understand what continuity means. But the point is that we just look at it, looks continuous, we say it's continuous, and then we feel good. Any questions about that? I have a few more notes on here for me to say something. The linearization, as you see the way I have it written there, L of xy equals 4y minus 2x plus 3. This is a function of x and y. Some of you are writing L of 1, 2 equals, thinking that that's notation for doing the linearization at the point. But that's not what we're doing. We're finding a full function that is the linearization at the point 2, 1. So there's no notation 2, 1 in that L, and for a different point, I would get a different L. So it's important that we know what point we're looking at when we write L, or else we don't know what the heck's going on. And some of you are also saying things like L of 2, 1 equals f of 2, 1, so I know I'm good. Well, this is probably function and my tangent plane, which is the linearization, always coincide at that point of interest. So that should always be true. The important aspect is that it approximates it away from that point. So away from that point, it's approximately equal. At that point, it's always directly equal. So hopefully we understand that a little bit better now. And the last thing I want to say is, sorry about not realizing that some of you were doing correct derivatives. I like X'd them out and I was like, oh, you happen to be getting the right answer, but no, it was just a simplified version of the derivative. So that's my fault. Okay, moving on to number 3. Again, I put the third way of really asking for what's going on here to verify a linear approximation. So we got any confusion about this out of the way here. What I mean is that the linearization of x cosine xy at 0, 0 is x. So you really have to go through the computations again in order to do that. And it looks like I didn't really write all my work down there for you, Pat. But anyway, we can use that to get the linearization just by plugging in. So the linearization is f applied at the point plus fx, x minus 0, fy, y minus 0, and that just comes out to be x. So that's verifying the linearization. And then I asked what I thought was a pretty interesting question is why does that make sense? And this was really open for discussion. So as long as you really attempt to give me some answer, I pretty much gave you points for it. If you forgot to say anything about it, it was a -1. But to me, why this linearization makes sense is that cosine is approximated by 1 near the origin. Cosine looks like this. So if I zoom in to the origin, this is going to be very close to 1. So when I do cosine xy times x, this should be approximately equal to x because cosine is approximately equal to 1 near the value 0. So that was my explanation of why that made sense. That just kind of popped in my head, so I put it down there. Not a big deal. Okay, number 4. What's going on here? We're using, let me get this guy to stop running. No, John, don't. Okay. So we came up with the approximate values for the partial derivatives in a previous homework. So I'm just recounting them here from a previous homework. And then we use those to do a linear approximation. So L now of FH is all that stuff, which comes out to a nice linear function in terms of just f, because my rate of change of h was 0, so it drops out of the equation. And then we're using that to approximate values of the function near that point. So here I think is a good illustration of the use of a linearization is to approximate a function, especially in this case where we actually don't know what that function is to plug in values. Like usually you say, well, why do I care about approximation when I can just use the function itself? Well, here I don't have the function, so the approximation is as good as I have, and it's a nice way to do that. If we look at 5565, that should be. I noticed somebody put this in their work. That should be right around this area because it's in between 50 and 63 and in between 60 and 70. So it should be right around here. So the value 1917 looks appropriate to be in here because it's in between these values. So this is really the best way of approximating those values when I don't have them, because we're saying that locally this thing looks like it's linearization, so if I plug into the linearization, that would give me a good estimate for the actual function. The notes I have for this problem is, number 1, I would appreciate if you use f and h instead of x and y, because it makes it more clear and makes it more applicable to the situation. But number 2, I really need you to be consistent. So if you use like f sub f and f sub h up here, and then you start started using X's and Y's down here, then I felt free to take points off because you're using two different labels for the same thing. So just, it helps me, and I think it helps you understand if you use the appropriate variables in a given situation.
See if there's anything else I wanted to say about this one.
No, that's all I wanted to say. Okay, so moving on, number 5. Also getting confusion out of the way here so that we don't mess up on the exam. I still had some people just drawing me the tree and not giving me the formulas. This is an easy problem on the exam, so make sure you do it right. We got the tree and then we have the formulas. And I just read the formulas off. There should be 2. So that's part of the problem is to figure out how many formulas you're actually writing, and it's always the number of variables that I have on my bottom level. I have 2 variables on my bottom level, so I should have 2 partial derivatives. I can think of W as a function of S and T, so I do dW ds and dW dt, and those formulas are as you see. That's just how it is by reading off of the tree diagram. And they should all be curly D's, so some of you are writing straight D's in certain situations. The only time we have straight D's is when we have single variable functions, which means I have a situation where I have a variable and I only have a single line coming down off of it. So in those situations, those are straight D's. Every other time should be curly. Since everything branches in my tree, everything here should be straight or curly D's. And then the last one is the number 6. I'm not going to go over that. I didn't put anything in the solutions about that. This isn't something I would put on the exam, but I'll just say that I was pleased for the most part with what I saw. There were some situations where a higher adaptive mesh would have been better. Sometimes I didn't even say anything, but I could see like little angles on there just very slightly, and it would be nice if they weren't there. But for the most part, good job on those. If you had some interesting behavior, it might be because of the relationships of the A and B that you chose. Like for instance, if you chose A equals B, then you're just going to get a straight line because you're plotting the same thing in X and Y. So if you did A equals B, then you're going to get X equals Y, which means that you're just getting the graph X equals Y. So the point was to choose different values, and I don't want to talk about what are good values to pick, but it does matter what you pick and how they relate to each other, so maybe think about that. Any more questions? All right. So what to do next? 20 minutes. We are going to do the integral. Oh,
What day is it?
the exam is Monday or Wednesday. If I get your homework graded over the weekend and get them back to you on Monday, then I will schedule it for the following Monday. If not, you'll get it Wednesday and it'll be that Wednesday.
Is it going to be across?
Okay, so last time we did this integral where the x integral was on the inside. Is that right? No, we did the x integral on the outside. That's the order that we did it, right? Okay, good. So we did that. is that we're calculating. So I don't know, you can get out your computers. It's not going to be too much fun. You can do that. Just plot x squared times y with my domain x going from 0 to 3, y 1 to 2. Nice looking graph. So looking at it from underneath, if we would just fill in all that area under, can't use that word area this time because it is just an area. But yeah, if I fill in that region underneath the surface to get a three-dimensional solid, the volume of that solid would be 27/2. Completely analogous to integrals in 2 dimensions. It would be nice if we had a way to actually fill that out so we could see the solid piece. I don't know a good way of doing that. I do know ways to create the sides so that we could create a solid looking thing by creating planes, and that's something that we actually do in Calc 4. So if you guys are moving on to Calc 4, we'll be drawing more three-dimensional pictures. What's that? Okay, so we computed this integral in one way, in another way. I'm going to compute it in a third way. The book waits till the end of the chapter to do this. I'm going to do it now, but I think that they have a good reason for waiting to the end. So I just want to try to make that clear after we do it. So the third way is to start really like the first way. So we always will essentially do integrals like this. So we're writing it as an iterated integral. But then rather than evaluate that integral, what I can realize is that since y is constant, since y is considered, since x is considered constant in this inside integral, I can actually pull it outside of the integral. So that looks a little strange, but what this means is that I can do this now as my inside integral, and whatever I get from this multiplies onto x squared, and then I have my outside integral. This is really the same way that we did it. When we computed that integral, we treated x squared like a constant. It just hung around and then got applied at the end. Well, that's what it's doing here. It's just hanging around and then getting applied at the end. So there's nothing too much new there. But here's where we get something new. Now if I view this as an outside integral, this guy is just a constant. Because that definite integral, when I evaluate it, whatever it is going to just come out to be a number. That's what definite integrals do. Because there's no x left over in there, I can actually pull that constant outside of the outside integral to get this. So I have transformed my iterated integral into the product of two regular integrals. integrating y squared gives me, or integrating y gives me y squared over 2 from 1 to 2, and that's multiplied on x cubed over 3 from 0 to 3. So I can do those integrals simultaneously. 4 over 2 is 2 minus 1/2. This is 9. 2 minus 1/2 is 3/2 times 9 is 27/2. So that's a sort of weird way of doing it, but it is a very much preferred way when we can do it, and the times when we can do it is when my original function splits as the product of two functions, one in x and one in y. So let me write it like this. In general, if my f of xy equals g of x times h of y, so if I can split it as the product of, again, those two separate functions, let me define an R. So with R, A, B, C, D, so that's just a setup for my integral, my double integral. I just do the same thing that I did here, just in generality. It will work. And I can write this as just the integral from A to B, g of x dx, times integral c to d, h of y. So if I realize f splits, then I can just do the split, write the integrals down, and multiply them together. I don't have to show this work. I just know that it's true. So the reason that they wait until the end is they don't want you to think that this happens all the time. So many times when I show students this, they think, oh, I can always do that. I don't need iterated integrals. But again, it only works if I'm splitting as the product of two things. So don't think that you're going to be able to do this too often. It's only in these special cases of somewhat simple functions. So what we should do is look at an example of a function that doesn't happen. Example 3. If I had a sum of products of functions like a polynomial like this. If I had a function like that, then I could use this if I split it up into two terms. So I could split the full integral up into two integrals term by term, and then do each of those by the products. So this would be one way that it would sort of mess up my way of splitting, but I could do it if I split into sums first. The better way of messing up what I want to do by splitting is to just give myself a non-polynomial function like sine and throw an x and y inside, and then I have no hope of ever splitting it up. Because those x and the xy is trapped inside of the sine function. I can never get it out, so I can never split this into a situation like that. So this is, again, I just want to emphasize, usually the situation is where I cannot do it that way and I have to do iterated integrals. So I know we only have a few minutes, 5 minutes. Let's just take a look at this problem. I don't know if we'll finish it. Pi in my rectangle is because I have trig functions, so it makes things work out nicely. but let's not focus on that too much. What we want to do here is we want to think which way will be better, because this is not a symmetric function. If this was xy times sine xy, it would be symmetric, and it wouldn't matter which way I do first. Integrals would be equally difficult or equally easy. But here, I have a non-symmetric function because I only have a y sitting out front. So the question is, which integral will be easier to do, dx or dy? All right. Dx. Why? I think that's right. If I do dx, then y is considered a constant, so that y out front is not going to contribute any difficulty to my integral, and I just need to be able to integrate sine of x times a constant. It's like sine 2x. This is very easy to integrate. By the way, what is the integral of sine 2x? I know it's tough. We have to let our brains backtrack in time. Wow, that was amazing. I had like 5 people tell me all at once. Get Christina. Very close. Yeah, we were saying the right thing. Everybody is motioning the right thing. That 2 should be on the bottom. The 2 should be on the bottom. Do I really need to write plus c here? I don't have enough room. Okay. So cosine 2x over 2. So this is what I call the, I don't know what I call it. I'm doing chain rule in integration, essentially is what it is. I'm doing the integral of the outside function divided by the derivative of the inside function. That's what I'm doing. And the reason we divide rather than multiply thinking integer values, but I didn't say it, so I wasn't like too upset when people gave me non-integer stuff. But when you use pi as a coefficient, then so if you use pi as a coefficient, that makes the period of this function 2, right? Because now 0 to 2 pi is going from 0 to 2 because the pi is there. But my period for this function is still 0 to 2 pi. So I have the period of one function is 0 to 2 pi, which is an irrational number. The period of another function is 0 to 2, which is an integer. So they never match up. What happens if you have two integers is that you eventually get the periods matching up because it should be the least common multiple. So if you use integer coefficients, the overall period should be the least common multiple of those in the GCD or something, but whatever. When I have two incomparable things, I think it does not even have a period. That it's just going to go forever and ever. So you can see that it kind of comes around and then stops. If you would keep it going, then you would just keep, and I think eventually it would just fill in the entire